Hey everyone, welcome back to the channel. If you're new here, don't forget to hit that subscribe button and ring the bell for more deep learning content. Today, we're diving into one of the most revolutionary concepts in modern AI, sequence-to-sequence models and the attention mechanism. This is a technology powering everything from Google Translate to ChatGPT. By the end of this video, you'll understand how these models work, why attention was such a game changer, and how it led to the transformer revolution. So, let's get started. All right, first things first. What exactly are sequence-to-sequence models, or Seq2Seq for short? Imagine you have a sentence in English, like hello world, and you want to translate it to French. Bonjour monde. Both are sequences of words, but notice something interesting. The input and output can have completely different lengths. That's the key characteristic of Seq2Seq models. These models take a variable length input sequence and transform it into a variable length output sequence. The input could be words, time series data, even audio waveforms. The output, also a sequence, but potentially a completely different length. The magic here is that the model learns this mapping automatically using neural networks. It figures out the complex relationship between input and output sequences through training. Seq2Seq models are used everywhere: machine translation, text summarization, chatbots, speech recognition, and so much more. Now you might be wondering, how does it actually work? Let's break down the architecture. The Seq2Seq architecture has two main components, an encoder and a decoder. Think of them as a team working together. The encoder's job is simple but crucial. It reads the entire input sequence word by word and compresses all the information into a single, fixed-size vector called the context vector. This vector is supposed to capture the complete semantic meaning of the input. Typically, we use recurrent neural networks, or RNNs, specifically LSTMs or GRUs for this. These are great at processing sequences because they have memory. Now, the decoder takes this context vector and generates the output sequence, also word by word. At each step, it predicts the next word based on what is generated so far and that context vector. So the flow is input sequence goes into the encoder, compressed into a context vector. The decoder uses it to generate the output sequence. Beautiful, right? But here's where things get interesting and problematic. This architecture has a major flaw, and it's called the Context Vector Bottleneck. Think about this. You're trying to squeeze an entire sentence, maybe even a paragraph, into a single fixed-size vector. Just one vector. Look at this sentence. The cat sat on the mat because it was very comfortable and warm. That's a lot of information, and we're compressing it into something like 0.23, negative 0.45, 0.89, just a bunch of numbers. This creates several problems. First, information loss. The longer your input sequence, the more information gets lost. It's like trying to stuff a suitcase. Eventually, things stop fitting. Second, performance degradation. Studies show that translation quality drops significantly as sentences get longer. Third, there's no selective focus. Every word in the input contributes equally to this one vector. But in reality, some words are way more important than others for specific output words. This bottleneck was killing the performance of Seq2Seq models on real-world tasks. We needed a breakthrough. And that breakthrough was attention, and I mean that literally. In 2014, Bottleneck and colleagues introduced a revolutionary idea. What if, instead of using just one context vector, the decoder could pay attention to different parts of the input at different times? Think about how you read and translate. When translating black cat to French as chat noir, you focus on black when generating noir, and on cat when generating chat. You don't treat everything equally. That's exactly what the attention mechanism does. Here are the key ideas. 1. Dynamic focus. The decoder can look at different input positions for each output word it generates. 2. No bottleneck. Instead of one fixed context vector, the decoder has direct access to all encoder hidden states. 3. Weighted combination. The model automatically learns important scores, attention weights for each input position. 4. Interpretability. We can actually visualize what the model is focusing on. This was huge for understanding neural networks. This was a complete game changer. Instead of one context vector for everything, we create a custom, specialized context vector for each output word. Mind-blowing. Okay, let's get into the mechanics. How does attention actually work step by step? Step 1. The encoder processes the input and produces a hidden state for each input word. So if you have 5 words, you get 5 hidden states: H1, H2, H3, H4, H5. Step 2. Now the decoder is at some time step t with its own hidden state, ST. It needs to decide which encoder states should I focus on. Step 3. We compute attention scores between the decoder state and each encoder state. This score tells us how relevant each input word is for the current output. Step 4. We apply softmax to these scores to get attention weights that sum to 1. Think of these as percentages. Maybe 70% attention on word 2, 20% on word 3, and 10% on word 1. Step 5. We compute a weighted sum of all encoder hidden states using these weights. This gives us our custom context vector for this specific decoding step. And finally, we concatenate this context vector with the decoder's hidden state to predict the output word. So it's a pipeline. Encoder states to score function to softmax to weighted sum to context vector to output prediction. And this happens for every single word we generate. Now, I know some of you love the math, so let's formalize this. First, we need a scoring function. The most common one is score equals H sub I transpose times W times S sub T. Here, H sub I is an encoder hidden state, S sub T is the current decoder state, and W is a weight matrix we learned during training. This score tells us the alignment between input position I and output position T. Next, we normalize these scores using softmax to get attention weights alpha. This ensures they're all positive and sum to 1. The formula is alpha sub Ti equals exp of the score divided by the sum of exp of all scores. Classic softmax. Finally, we compute the context vector C sub t as the weighted sum of encoder hidden states. It's just sum of alpha sub Ti times H sub I. Don't worry if the math seems dense, the intuition is simple. Score how relevant each input is, normalize those scores, then create a custom context by mixing the inputs according to those scores. Let's see attention in action with a real example. We're translating the black cat into French, le chat noir. Notice that French puts the adjective after the noun, unlike English. When the decoder is generating the word noir, which means black, where should it look in the input? Exactly, it should focus on the word black. And look at the attention weights here. The gets 0.05, very low attention. Black gets 0.85, super high attention. Cat gets 0.10, low attention. The model automatically learned that to generate noir, it should focus almost entirely on black. Similarly, when generating the word la, it focuses on the with 92% attention. When generating chat, it focuses on cat with 88% attention. This is the beauty of attention. It learns these alignments automatically from data, even when word orders completely change between languages. Now here's where it gets really exciting. Researchers thought, if attention is so powerful, what if we just use only attention? That question led to the transformer architecture in 2017 with the famous paper Attention is All You Need. Transformers throw away the RNNs entirely and use something called self-attention. Here, each word in the sequence attends to every other word, including itself. This had massive advantages. One, parallelization. Without RNNs processing sequentially, we can process the entire sequence in parallel. Training became way faster. Two, multi-head attention. We use multiple attention mechanisms in parallel, allowing the model to focus on different aspects simultaneously. Three, positional encoding. We add position information directly to the inputs so we don't need RNNs to handle sequence order. And this, my friends, is the foundation of everything in modern AI. BERT, GPT-3, GPT-4, ChatGPT, Claude, Google's Palm, they all use transformers. The evolution went RNN plus attention to pure attention, or transformer, to modern AI revolution. And it all started with that simple idea of paying attention to different parts of the input. For the coders in the audience, let's look at some actual PyTorch code implementing attention. Here's a simplified attention decoder. In the init method, we define our attention layer as a linear layer that takes twice the hidden size because we're combining encoder and decoder states. We also have a GRU decoder and an output layer. In the forward method, here's where the magic happens. First, we calculate attention scores by concatenating the decoder hidden state with each encoder output, then passing through our attention layer. Second, we apply softmax to get attention weights. Third, we compute the context vector by taking a weighted sum of encoder outputs using these attention weights. Fourth, we feed this context into the decoder GRU along with the previous decoder state. Finally, we pass the decoder output through a linear layer to get our predictions. This is a simplified version, but it captures the core idea. In practice, you'd add more bells and whistles, but this is the foundation. I'll put a link to a complete implementation in the description if you want to try building this yourself. All right, let's recap everything we've learned today. 1. Seq2Seq models map variable length inputs to variable length outputs. They're the foundation of many NLP tasks. 2. The classic encoder-decoder architecture compresses input into a fixed context vector, which the decoder uses to generate output. 3. This creates a bottleneck problem. One vector can't capture long sequences effectively. 4. Attention solves this by letting the decoder dynamically focus on relevant input parts at each step. 5. The mechanism works through scoring, softmax normalization, weighted sum, and context creation. 6. Attention became the foundation for transformers, which revolutionized AI. 7. Applications are everywhere. Translation, summarization, chatbots, question answering, and basically all modern NLP. The key insight is this: attention changed everything in AI. It solved a critical problem and opened the door to models we never thought possible. And that's a wrap. I hope you now have a solid understanding of Seq2Seq models and the attention mechanism. If you found this helpful, please give this video a thumbs up and subscribe for more deep learning content. Hit that bell icon so you don't miss future videos. Drop your questions in the comments below. I love discussing this stuff. Thanks so much for watching, and I'll see you in the next video. Until then, keep learning, keep coding, and keep paying attention.